In this lecture, we will discuss about the standing waves in organ pipes. What are organ pipes? Organ pipes are the musical instruments which are used for producing sound when air is blown into them. We have got two types of organ pipes. One is open organ pipes and closed organ pipes. Open organ pipes are open at both the end, and closed organ pipes are open at one end only. Let us firstly discuss the closed organ pipes, their analytical treatment of production of standing waves. We know from the previous lectures or analytical treatment of the stationary waves in strings, what is the equation for the stationary waves? Yx of t is equal to minus 2r sine of kx cos omega t. Here the analytical treatment is the same, but to make a difference we will replace y by s. So in case of the standing waves produced in the organ pipes, we have got sx of t is equal to minus 2r sine of kx cos of omega t. So the equation in the standing waves is same in both the cases, but to make it different we replace that y with the s. This s says these are longitudinal stationary waves and the y tells us these are transverse stationary waves in strings. We have to see how the standing waves are produced in closed organ pipes. Taking the closed organ pipe, it is open at one end and closed at another. So here x is equal to 0, here x is equal to L. We are always, in case of organ pipes, we are always having an antinode at the open end, and in the closed organ pipe we are having a node at the closed end. At x is equal to 0, we are having a node. That means at x is equal to 0, sx of t is equal to 0. Now, at x is equal to L, we are having an antinode. That means sine of KL is maximum. Maximum value of sine of any angle is equal to 1. That means when sine KL is equal to maximum, it got to be the sine of odd integral multiple of pi by 2. So we have sine of KL is equal to sine of 2n minus 1 into pi divided by 2. This is odd integral multiple of pi by 2, where n starts from 1, 2, 3 or so on. Moving on, we have KL is equal to 2n minus 1 pi divided by 2. We know that k is a propagation constant, it is equal to 2 pi divided by lambda into L is equal to 2n minus 1 pi divided by 2. Pi cancels out. Here we have got lambda is equal to, cross multiplying it, lambda is equal to 4L divided by 2n minus 1. This is the wavelength of the longitudinal stationary waves which are set up in closed organ pipes. Now we will look at the fundamental mode and at the overtones. For finding the lambda and the frequency of the fundamental mode or the first harmonic, we have to replace n by 1. So for first harmonic n is equal to 1, which gives us lambda is equal to 4L. So L is equal to lambda by 4. Now this tells us in the whole length, a quarter wavelength of the longitudinal stationary wave is produced. To show it, that is shown by, this is the fundamental mode. Here it is a node, here we are having antinode. Now the frequency of the fundamental mode nu1 is equal to V divided by lambda 1. Taking it as lambda 1, V divided by lambda 1, that is equal to V divided by 4L. So V divided by 4L is the frequency of the fundamental mode or the first harmonic. For second harmonic, second harmonic, replacing n by 2. So we have lambda 2 is equal to 4L by 2 into 2 minus 1. That is 4L by 3, which gives us L is equal to 3 by 4 lambda 2. That means for the first overtone or second harmonic, we have got 3/4 of a lambda or 3/4 of a wave in the closed organ pipe. That means we are having this shape. This is lambda by 4, this is another lambda by 4, this is another lambda by 4. That means it is 3 lambda by 4. So here we are having a node x is equal to 0. Here we are having an antinode. Here we are having an antinode. Here we are having a node. Talking of the frequency, so frequency of second harmonic or first overtone, nu2 is equal to V divided by lambda 2, and lambda 2 is equal to 4L by 3. 3 comes up in the numerator, that is 3 V divided by 4L. We know that V divided by 4L is the fundamental frequency or frequency of the first harmonic. So replacing V divided by 4L by nu1, we have nu2 is equal to thrice nu1. Now coming on to the third harmonic or second overtone, we have to replace n by 3. So we get that lambda is equal to 4L by 2 into 3 minus 1. That is 4L divided by 5. It is lambda 3. That means L is equal to 5 divided by 4 lambda 3, which brings us to the conclusion that in a length L of the closed organ pipe, we will be having a wave and a quarter. A wave and a quarter. So it can be shown like this. It is the third harmonic or second overtone, second harmonic or first overtone, fundamental mode or first harmonic. Here n is equal to 1. Here n is equal to 2, here n is equal to 3. Now seeing the frequency, calculating the frequency in this one. So nu3 is equal to V divided by lambda 3, as the velocity is constant. So V divided by lambda 3 is equal to 4L by 5. 4L by 5. This 5 goes to the numerator. So 5V divided by 4L. We know that V divided by 4L is the fundamental frequency. So nu3 is equal to 5 times nu1. From the discussion we see that the fundamental frequency is nu1. The frequency of the second harmonic is 3 times nu1. And the frequency of the third harmonic is 5 times nu1. That means we are having only the odd frequencies. Or we can say that to calculate the frequency of the nth harmonic, Vnth is equal to 2n minus 1 into nu1, where nu1 is the fundamental frequency. For second harmonic, n is equal to 2, which gives us thrice nu1. For third harmonic, n is equal to 3, which gives us 5 times nu1. So it is the general formula for calculation of the frequency of the nth mode. The frequency of the nth mode is odd integral multiple of nu1, that is 2n minus 1 nu1. We can also say that nu-n is equal to 2n plus 1 into nu1. It is also the odd integral multiple, but let us see the difference. Here n starts from 1. Here n starts from 0. This is the difference between the odd integral multiple written as 2n minus 1 or 2n plus 1. Thank you.